Sometimes tech can feel stagnant, so I thought learning a new programming language would be a good way to stay excited about technology. It worked, and I ended up building some pretty cool simulators that model natural biological processes, and I did it on a Steam Deck. This video is the story of learning a new programming language and using it to develop out two separate simulators. The first, a cellular automaton, and then a colony optimization algorithm to simulate route finding and optimization in an unmapped space. It's an empowering feeling to learn a new programming language. They're all a little different, and learning a new one can feel a little bit like discovering a powerful tool, and it gives you an entirely new lens to look at problems through. But when I think back on the timeline of languages I've picked up, I tried many in my early career, but somewhere in there I mostly stopped learning new ones. I continued to learn the languages I used at depth, and there's a lot to be said for a depth of knowledge with a specific tool, but it can also stagnate your approach to solving problems, and everything starts looking the same. I want to keep learning and growing, so I purposely set out to learn a new language. Which language, though? Looking through the huge list of possibilities, and there are a lot of them, I set out a couple of tenets to help me hone in on a few choices. There are many languages I don't know that have been around for a long time, but I'm mostly curious about modern languages, so I focused on languages that have been designed in the last decade. There are a lot of special purpose languages and languages tied to a specific technology, but I wanted a general purpose language. This left me with a lot of great options still, some of them very popular, but I always root for the underdog and look for hidden gems, so I got excited when I found Crystal. Its syntax is really close to Ruby, but it's actually a compiled language with static type checking. What intrigued me the most is its type inference system. It gives the lightweight feeling of a dynamically typed scripting language, but you supposedly get the speed and safety of a statically typed compiled language. We'll go into more details on this magic type inference system while we build the simulators. The documentation looked great, and I couldn't wait to get started. Windows isn't officially supported, so I'd use a Linux install, which made me want to try something I'd been thinking about. How would it be to develop on the Steam Deck? If you're not familiar with it, the Steam Deck is a handheld gaming device by Valve that runs its own version of Linux called SteamOS. At its core, it's a fairly high-powered x86 computer in a handheld form factor. I've only used it for gaming, so this is a great way to see how it can flex as a development machine. Getting Crystal installed on the Steam Deck and getting a Hello World program took literally minutes. It was dead simple, well-documented process. Crystal files can be ran directly from the command line, or you can compile them into a standalone executable that loads much faster. I could tell right away that developing on the Steam Deck was going to work out just fine. The display is running on an external 4K monitor as well as its built-in monitor, and it's as smooth as any desktop computer. As a bonus, the Steam Deck uses KDE Plasma Desktop, which ships with Kate, which has been a favorite text editor of mine for literally decades, so I'll use that for development. Now that I have a running environment, my goal in the next step is to learn about the language itself, built-in data structures, how to do I/O, etc. After thinking about what project to do, I thought back to one of the first programs I learned in Computer Science 101, Conway's Game of Life. This is possibly the first form of computational life simulation, and the first one we'll build today, so let's talk about what it is for a moment. The Game of Life is a cellular automaton, which is a type of discrete mathematical model that was among the first systems to simulate lifelike behavior. It does this by applying a few basic rules of life. Consider a two-dimensional world made up of adjacent cells. If we populate the cells with an initial state of alive or not alive, and then we continually apply a simple set of rules to each cell, we'll see lifelike patterns emerge. Live cells with one or less neighbors dies from underpopulation. Live cells with 4 or more live neighbors die from underpopulation. Live cells with 2 or 3 live neighbors is repopulated. Dead cells with exactly 3 neighbors become live from reproduction. If you keep repeating these steps, some interesting patterns start to emerge, and when you scale it up, These emergent behaviors have been used to model real-world scenarios and solve problems in physics, chemistry, cryptography, and many other fields. I'll use a modification to the game of life called Brian's Brain. It adds one additional state, dying. So the rules are, dead cells turn on if it have exactly 2 neighbors that were alive. All alive cells go into the dying state. All dying cells go into the dead state. A few years ago, I built one of these with the Godot game engine for a game jam on itch.io, so I thought this would make a really simple first program to learn a little bit about how Crystal works. Now for the implementation. Let's break the problem down. At the heart of it, you have a grid world where each cell can be in one of 3 states, alive, dying, or dead. If we use a 2-dimensional array to represent the grid world and an enum to define the states, a simple state machine can transition the grid at each timestamp. So I dove in and wrote my first Crystal code. The code I ended up with looks different than what I started with, but this is what I came up with. I created an enum called states and a class called brain that holds a 2D array of states. The first thing to note about Crystal is that you don't use braces or indentations to outline block statements like conditionals, loops, functions, and classes. Instead, the end symbol is used to terminate all block statements. The @ sign denotes a member variable like self in Python or this in Java. Next, I made a member function to randomly populate the initial states. One of the things that confused me about Crystal at first is the lack of a for loop with the traditional construct, the kind that directly provides for an initialization, incrementer, and terminating condition. I started off using hand-rolled while loops that looked pretty messy, but later in the process I picked up on using ranges and do loops to iterate through array indexes, and it really makes the code much more readable. It was very easy to refactor using this pattern, so you'll see a mix of them while I'm developing. This is a good place to talk about the super powerful type inference system in CrystalLang. You can be explicit about a variable type at creation, or you can simply assign it a value and Crystal will infer the type. If you try to assign an incompatible type, it will complain. It's an amazing feature. Next, I added the tick function to handle time steps. This is where the simple state machine lives. I also made a function to count neighbors for dead cells. In CrystalLang, you don't have to use parentheses in function calls if you don't want to. I wanted to be able to view the simulation, so I made a function to print out the ASCII values. Then I discovered that Crystal ships with a library that helps you colorize the output. This delighted me. The small things make a difference. I wanted to be able to run the simulation at different sizes and speeds, and found that Crystal also ships with a very capable options parser. In just a few minutes, I had it accepting user input from the command line. So let's see how it runs. This is the output in a standard Linux terminal. There were some flickering issues, but that was improved with a little buffering. You can see that the types of patterns we expect in a cellular automaton are emerging. Overall, it's working as expected. This is pretty cool. The logic running this entire simulation is less than 100 lines of code and only took a few hours to write and refactor. This is my first full program built in Crystal, and I have to say that I'm impressed. It was simple to figure out how to get things done. I love the terse syntax. It feels liberating. Okay, now I wanted to take on a larger challenge, something I had never built before, so the challenge wouldn't just be about using the language to solve a problem I already know the solution for, but more about how the language assists me in developing all new solutions. So what problem to solve? We walk a lot because it's good exercise, it gets you out in the world, and it gives you time to think. One of the things I think about is how people decide which way to go and what's the most optimal way to get from where they started to where they want to be. In a way, it's pretty easy for us because we have digital maps of the world and we know where our destination is, so it's a matter of picking from available routes. Let's talk about a more difficult navigation scenario for a moment. Imagine a world with many obstacles, and you need to find an optimal route to a target. You don't know where the target is though, and you don't have a map of the world. All you have is a starting point, and you can only see the next step around you. If you don't have a mental map and you can't effectively use visual cues, how do you find the target? And once you do find it, how would you know that you had found an optimal route? What if obstacles were dynamic so that routes could become blocked or unpassable? So this is really a route finding and optimization problem, and to solve it, I'm taking ideas from the way real-life insects solve the exact same problem. Ant colony optimization is a set of algorithmic approaches that have been used to solve route optimization problem, like the traveling salesman problem. Let's discuss that one briefly to investigate how difficult navigation optimization problems can be. It simply asks, given a list of cities and the distance between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the origin city? Humans are very good at solving this because of our spatial logic skills, but computers are not. It's what's called an NP-hard problem. This means that if you tried a brute force approach where you looked at every possible combination and calculated the shortest distance path, it becomes computationally impossible very quickly. For 4 cities, you only need to calculate 6 paths, but for 8 cities, you need to calculate about 5,000 paths, and for 16 cities, over 1.3 trillion unique paths. You can see that finding the exact shortest path is computationally impossible, and this is where we look at how nature has already solved this problem with colony optimization. Think about the natural processes of colony insects. When they move through the world, they use pheromones to communicate with each other. When an ant's found a food source, they'll leave pheromones on the ground as they return to the colony. This helps other ants find the food source. In the traveling salesman problem, many independent agents are turned loose on the graph to explore paths. They drop digital pheromones at each node, with the main idea being that the shortest paths will have the strongest pheromones on them. Now let's bring this concept back to the world I described. It's a bit different because we don't have a list of nodes and their distances. We have a 2D grid with a starting point and a target, and we can only see what is immediately around us. The end problem is still basically a navigation optimization problem, so we can use the same biological approach of colony optimization to find optimal routes in a world we're blind to. Here's how I did it. The first thing we need is a world full of obstacles that we'll try and find paths through. To handle this, I created a class called World that holds a 2D array of type called Tile. That's a data object representing a square area of the world. Each tile holds a pheromone level, some metadata, and pointers to the neighboring tiles, as well as the cost of transitioning to those neighbors. I initially made a set of functions to assign random elevations, and then some functions to segment and smooth the technology. I'll change that approach later in development to something that should have been more obvious. So now I have a world, but I don't have a way to visualize it easily. I made an ASCII display for the cellular automaton demo, but I wanted something better for this. Crystal doesn't have a built-in user interface toolkit, but it does come with a built-in web server, so I turned to my old friend JavaScript and built out a simple UX based on HTML canvas. This was super easy to do. I just created a URL parser, and it was simple from there. JSON is included in the box with Crystal, so I didn't have to install any add-ons to make this work. Wrapping the program with a web API took literally minutes. Now that I have the topology set up, I added a couple of functions to pick random points for the colony and the target. I made it so they pick opposite sides of the map. These show up on the display as yellow or blue for the colony and red for the target. Next, I need a colony controller. I lean into the metaphor a little and call this the queen. They are responsible for starting the sim, creating agents, and expiring agents that have lived past their allotted ticks. They orchestrate the state of the colony at each tick. Next up, I made the insects, or agents as I called them. Think of them as the colony ants that go out into the world in search of food sources. These agents will travel through the world in search of the target. They each have a set of genetics, or metadata, that controls their decisions. This gets fuzzed at birth, so they each behave a little bit differently. They basically wander around the world using a set of meta-heuristics, generally preferring tiles that are lower cost and placing the highest value on tiles with the most pheromones. If they find the target, they'll replay their own approach track to get back to the colony, smoothing out any open loops in their path. As they return to the colony, they leave a decreasing amount of pheromones on each tile. This helps other agents find the target since they prefer higher levels of pheromones. As paths are traced over, the shortest should win out since they're the freshest. On the display, tiles with high levels of pheromones are bright red, while tiles with lower levels fade to black. Pheromone levels are globally decayed at each tick. That's it. That's all there is to this algorithm. After working through some edge cases, the simulation started producing results. The code went through a bit of refactoring as I learned how to make things more efficient and readable in Crystal. What struck me was how surprisingly little code was needed to come up with pretty good results. In fact, most of my code was in the terrain generation and refinement functions, and when I wanted to add a function to move the topology around to see how the colony adapted to broken roots, it dawned on me that I'd been going about this all wrong. Thinking back to the cellular automaton I had just created, why couldn't I use that to generate the terrain? It creates features of live and dying cells on a background of dead cells, and the features move continuously from one tick to the next. I returned to the game of life code and updated the API a little, and then included it as a terrain generation and evolution mechanism. Using the game of life simulation to generate and evolve terrain worked great and really simplified my codebase. After a little tweaking, the agents were quite successful at repairing broken roots. The basic JavaScript UI worked great in visualizing the solutions. Still, I wanted something more immersive to demonstrate the full simulation, so I decided to use the same API and build a 3D representation of the simulation using the Godot game engine. It took a couple of evenings to put it all together, but essentially it procedurally generates the height map for the board and the agent state from the exact same JSON API that feeds the JavaScript UI. Let's look at some examples. I've watched this thing run for hours now, and the agents generally find a fairly optimized path. Sometimes the path becomes more optimized over time. It amazes me that a few simple heuristics can be used to solve this problem, and I think it's a rather elegant solution too, to build off the concepts from the natural world. When the world changes around them, they tend to do a good job of repairing the path, but these solutions become less optimal the more times you alter the landscape. For the most part, the simulation works to find good routes in an unknown space. I'm not claiming this is the best approach, but it seems to generally work for finding your way in a world that you're blind to. There are certainly many improvements and optimizations that can be made too, like smoothing out small crooks in the lines and tuning the agent's heuristics. I'll leave those for future videos though, because I do see myself building on this simulation a bit. What are my thoughts on Crystal? Well, they're extremely positive because it was a delight to work with. I loved how the language got out of my way so I could focus on the problem. The syntax is easy to read and easier to write, and things just got better the more I learned. The ultimate question would probably be, will I consider using Crystal to solve the next problem? The answer is absolutely. It'll go to the top of my list moving forward. It was a delight to work with, and there's a good chance it'll become my go-to language over time. 5 out of 5 stars. What about programming on the Steam Deck? Well, it's a fairly powerful Linux desktop in a handheld form factor, and it worked like a charm. It's got the power of a desktop with the portability of a handheld, which means I could easily move it around to the different workspaces I use with no fuss. 5 out of 5 stars. Making the automatons in this video was a lot of fun. I learned a lot and it gave me new ways to think about problems. I see a lot of simple tweaks that could make this simulation perform better, so I'm excited to follow this one up. I'd love to hear your thoughts on this in the comments. Thanks so much for watching. I hope you enjoyed it. Keep learning, keep growing, and keep making stuff.